In the vast expanse of our solar system beyond the giant planets, lies a realm of icy bodies and celestial mysteries. It was in this distant region back in 1930 that a young astronomer named Clyde Tombaugh made a groundbreaking discovery. Tombaugh, working at the Lowell Observatory in Arizona, meticulously scanned photographic plates of the night sky, searching for a faint, elusive object. His persistence paid off when he detected a tiny speck of light that moved against the background stars. This tiny speck, later named Pluto, would captivate the imagination of astronomers and the public alike for decades to come. Pluto's discovery was a testament to the power of human curiosity and ingenuity. It expanded the known boundaries of our solar system and hinted at the existence of a vast, unexplored region beyond the giant planets. At the time of its discovery, Pluto was hailed as the ninth planet, a distant and enigmatic world that seemed to complete our solar system's planetary family portrait. Little did anyone know that Pluto's classification as a planet would be challenged decades later. However, for the time being, Pluto reigns supreme as the distant ruler of the solar system's outer reaches. Pluto, the once and future king of the Kuiper belt, is a world of icy mystery and surprising complexity. Smaller than Earth's moon, Pluto is a dwarf planet with a diameter of about 2,377 kilometers. Its surface, a mosaic of frozen nitrogen, methane, and carbon monoxide, reflects sunlight with a reddish hue. Despite its diminutive size and frigid temperatures, Pluto is a world of unexpected diversity. Its surface is a tapestry woven with craters, vast plains, towering mountains, and flowing glaciers. These features hint at a dynamic world shaped by both internal geological processes and external forces. Pluto's surface is also home to a vast, heart-shaped region known as Tombaugh Regio, named after Pluto's discoverer. This region, a nitrogen glacier spanning over 1,000 kilometers, showcases the incredible diversity and complexity of this distant world. Despite its distance from the Sun, Pluto is a world that is constantly changing and evolving. Pluto's story is inextricably linked with that of its largest moon, Charon, a celestial companion locked in a gravitational dance. Charon, discovered in 1978, is a massive moon relative to its host planet, with a diameter of about 1,208 kilometers. Pluto and Charon are tidally locked, meaning they always show the same face to each other as they orbit their common center of mass. This gravitational embrace creates a fascinating dynamic between the two worlds. Their orbital dance, a celestial waltz lasting 6.4 Earth days, is a testament to the power of gravity to shape the destinies of celestial objects. The Pluto-Charon system is often referred to as a binary system, a term used to describe two objects of comparable mass orbiting a common center of mass. The story of Pluto and Charon is a reminder that space is filled with intricate relationships between celestial objects. Beyond the realm of the giant planets, past the orbit of Neptune, lies a frigid and mysterious region of our solar system known as the Kuiper belt. This vast donut-shaped region, extending from about 30 to 55 astronomical units from the Sun, is home to a plethora of icy bodies, remnants from the early solar system's formation. The Kuiper belt is a celestial treasure trove, offering astronomers a glimpse into the conditions that prevailed during the solar system's infancy. The Kuiper belt is believed to contain hundreds of thousands of icy objects larger than 100 kilometers in diameter, as well as trillions of smaller objects, including comets. These objects, composed primarily of frozen volatiles such as water ice, methane, and ammonia, are thought to be pristine remnants from the solar system's protoplanetary disk. The Kuiper belt's significance extends beyond its role as a repository of primordial material. In 2006, the International Astronomical Union, or IAU, made a decision that sent shockwaves through the scientific community and beyond. Pluto, once considered the ninth planet in our solar system, was reclassified as a dwarf planet. This decision, while based on scientific evidence, sparked a debate that continues to this day. The IAU's decision to reclassify Pluto was based on a new definition of the term planet. According to this new definition, a planet must meet three criteria. It must orbit the Sun, it must be massive enough for its own gravity to pull it into a spherical shape, and it must have cleared its orbital neighborhood of other objects. Pluto meets the first two criteria but fails to meet the third. Its orbit, located within the Kuiper belt, is shared with numerous other icy bodies. Despite the controversy, the IAU's decision stood, and Pluto was officially reclassified as a dwarf planet. As a dwarf planet, Pluto became the archetype for a new class of objects in our solar system. In 2006, the same year that Pluto was reclassified as a dwarf planet, NASA launched a spacecraft on a mission that would forever change our understanding of this distant world. The New Horizons mission embarked on a 9-year journey to Pluto, carrying with it the hopes and dreams of scientists and space enthusiasts around the world. The New Horizons spacecraft, a marvel of engineering, was designed to travel at incredible speeds, covering the vast distance to Pluto in record time. It was equipped with a suite of 7 scientific instruments including cameras, spectrometers, and plasma instruments designed to study Pluto's geology, composition, atmosphere, and its interactions with the solar wind. On July 14, 2015, after a journey of over 9 years and 3 billion miles, New Horizons made its historic flyby of Pluto. The images and data that New Horizons sent back to Earth were nothing short of breathtaking, revealing a world far more complex and dynamic than anyone had imagined. The New Horizons flyby of Pluto in 2015 was a watershed moment in our exploration of the outer solar system. The data and images beamed back to Earth by New Horizons painted a picture of Pluto as a surprisingly complex and dynamic world. One of the most striking discoveries made by New Horizons was the diversity of Pluto's surface. Far from being a uniform expanse of craters, Pluto's surface is a mosaic of different terrains including vast nitrogen glaciers, towering mountains of water ice, and craters of various sizes and ages. This diversity of features suggests that Pluto is geologically active, with processes such as tectonism, erosion, and cryovolcanism shaping its surface over billions of years. Another surprising discovery was the presence of a thin but complex atmosphere surrounding Pluto. New Horizons observed evidence of atmospheric hazes, nitrogen snow, and even possible clouds, indicating that Pluto's atmosphere is far from static. After its historic encounter with Pluto, the New Horizons mission wasn't finished. With its fuel reserves still intact and its scientific instruments operating flawlessly, New Horizons embarked on a new mission to explore the Kuiper Belt. On January 1, 2019, New Horizons flew past a small peanut-shaped Kuiper Belt object called 2014 MU-69, later nicknamed Arrokoth. This flyby, the most distant ever conducted by a spacecraft, provided scientists with an unprecedented close-up view of a pristine Kuiper Belt object. Arrokoth, with its 2 distinct lobes that appear to have gently merged together, provided scientists with evidence supporting a model of planet formation known as hierarchical accretion. The New Horizons flyby of Arrokoth was a testament to the ingenuity of the mission team and the spacecraft's remarkable capabilities. The Kuiper Belt, a vast repository of icy bodies beyond Neptune, is like a time capsule, preserving remnants from the early solar system's formation. Studying these objects offers astronomers a unique opportunity to peer back in time, unraveling the mysteries of our solar system's birth and evolution. Each Kuiper Belt object holds clues to the conditions that prevailed in the protoplanetary disk, the swirling cloud of gas and dust that gave rise to our sun and planets. The composition of Kuiper Belt objects, primarily frozen volatiles such as water ice, methane, and ammonia, provides insights into the chemical makeup of the early solar system. By analyzing the ratios of these volatiles, astronomers can learn about the temperatures and pressures present in the protoplanetary disk. The distribution and orbital characteristics of Kuiper Belt objects also provide clues about the dynamical evolution of the early solar system. The Kuiper Belt is a region of ongoing discovery, with new objects being discovered all the time. As telescopes become more powerful and our ability to explore the outer solar system improves, we can expect to learn even more about this fascinating region.